We finished last time with an example of calculating an electric field both inside and outside a spherical shell. We found that the field inside was 0 down within this region because there's no charge enclosed. And we found that the field outside looks like a point charge. Let's move on, just so you don't think that all we use are spherical examples. Let's find an electric field with the following configuration. Suppose I have an infinite line of charge, of uniform charge per unit length, or linear charge density lambda, so charge per meter. Suppose I want to find the electric field at some point P. And let's say that it's located some distance, little r, from the infinite line of charge. Now you might say, infinite line of charge, this is impossible. No, actually it really isn't. We can solve this problem fairly readily. But in this case, we can't use a sphere. A sphere doesn't provide us with the proper symmetry to deal with a line of charge. What we're going to do in this case is to draw a Gaussian cylinder. And I'm going to draw a Gaussian cylinder like so. It's going to have a radius r, just like the distance from the point to the line. And it's going to have some arbitrary length L. Now mind you, when we finish the calculation, L should not be present. L should have canceled out because it can't be a part of the answer. So, once again, let's use Gauss's law. Integral B dot dA is equal to Q enclosed over epsilon naught. In this case, if I want to find the electric field up here, it's going to be, E is going to be constant at every point on the curved surface of the cylinder. And it's going to point radially outward from that surface so that, as will dA, so that E and dA, it's going to be the same method. E is constant at every point on that surface. E and dA are parallel at every point on that surface, so I can immediately write E times the integral of dA is equal to the charge enclosed. How much charge am I enclosing? Well, I'm enclosing lambda times L amount of charge. Right? Because the cylinder is enclosing from here to here, it's enclosing a linear charge per length lambda times L. Integral of dA for the cylinder is just the area of a cylinder. The area of this cylinder is going to be 2 pi r times L. And so that'll be equal to lambda L over epsilon naught. As I promised, the L's will drop out. And of course, E then is equal to lambda over 2 pi epsilon naught times r. Beautiful. Works very nicely. Now, if the line of charge were finite, this method wouldn't work because we'd have to worry about the end caps, and we have to worry about the fact that the electric field is not perpendicular to the cylinder at all points. So this only works for an infinite line of charge to use this particular method. Let's look at a non-conducting infinite sheet of charge. Let's say I have an infinite sheet of charge, uniformly distributed, and I want to find the electric field someplace near but outside the sheet of charge. So we'll call that point P there. Again, a Gaussian cylinder is going to be our best bet. It would be, so I would draw it this way and encompass this point. Notice, in this case, I could say E, integral of E dot dA is equal to the charge enclosed divided by epsilon naught. The charge that's enclosed is going to be the charge per unit area of my cylinder times the area of my cylinder. On the left-hand side, I have flux going in two directions, this way and this way. Therefore, I can say 2 times E times the area is equal to sigma times the area. And so the electric field at that point would be sigma times, this should be over epsilon naught, sigma over 2 epsilon naught. So it's a very simple calculation. Don't even have to calculate an area in that case. So those are some nice examples of uniformly charged surfaces and using Gauss's law to calculate a field for that. Let's move on to touch on some other notions where Gauss's law applies. Let's talk about conductors. Those guys were insulators. Let's talk about conductors in electrostatic equilibrium. In conductors, electrons are free and they're highly mobile. In things like copper and other metals. So in electrostatic equilibrium, there's no net motion of charge within the conductor. What does that mean? So if I have a conductor and I want no net motion of charge, the charge, let's say it's a positively charged conductor, the charge in the conductor is going to get as far away from, each charge will get as far away from the other charges as possible. What that means then is all of the charge in the conductor will reside on the surface of the conductor. So that's one property of a conductor that you want to remember. What that means by Gauss's law is, no matter where I draw my Gaussian surface inside the conductor, I'm enclosing zero charge. Therefore, the electric field is zero inside the conductor. Even if I'm just a tiny fraction away from the surface, it's still zero. The electric field just outside the conductor is perpendicular to the surface and has a magnitude of sigma over epsilon naught. Just do the last problem we did with only a cylinder going in one direction, and you'll see that you get that same answer. If I have irregularly shaped conductors, what's going to happen there is the charge is going to tend to accumulate near the sharpest points. Kind of how a lightning rod operates. A rod with a very sharp point. That's where the charges are going to accumulate. Now, what we can do with this is that we can say, well, could it possibly be another way? No, if there were some component of the electric field, for example, that was tangential rather than normal to the surface, well, that would mean the charges would move. And we've already said in electrostatic equilibrium, the charges don't move. So the electric field for this conductor can only point in a direction normal to the surface. So these are some properties of conductors that you might want to remember. Let's do a nice example of this. Suppose I have a sphere, let's call it a conducting sphere, inside a conducting shell. And let's say that the sphere has a radius little a, the inner shell has a radius little b, the outer shell has a radius little c. So I have a conducting shell and a conducting sphere. Let's say that the charge on the inner sphere is plus 2q, and let's say that the net charge on the shell is minus q. What I want to do is find the electric field for r less than a, r between a and b, r between b and c, and r greater than c. And I want to find the charge on each shell surface. Okay? Tall order, but we can do it. First part, what is the electric field for r less than a? Well, if it's a conducting sphere, the sphere contains no charge inside. It's all on the surface. So if I draw a Gaussian surface inside my conducting sphere, I'm enclosing no charge whatsoever. So for r less than a, the electric field has to be 0. I'm enclosing no charge. What about in between, where a is less than r is less than b? So maybe somewhere out here. I can draw a Gaussian surface at some distance little r. And I can say, okay, how much charge is this Gaussian surface enclosing? Well, it knows nothing about this shell whatsoever, so the shell doesn't even matter. It's enclosing plus 2q because it encloses the entire sphere. So the electric field then, I can, once again, it's going to be constant all at every point on that surface. The area vector is going to be parallel to the electric field. So once again, it's just E times the area is equal to the charge enclosed, which is 2q over epsilon naught. The area of that Gaussian sphere is just 4 pi r squared equals 2q over epsilon naught. So my electric field for r less than b but greater than a is going to be q over 2 pi epsilon naught r squared. How about within the conducting shell? Within the conducting shell, so that is to say, for r between b and c, the shell is a conducting shell, therefore the charges lie on the inner surface and the outer surface, but there's no charge enclosed in between. What that must mean is that the field inside the shell, so E for B less than R less than C, also has to be 0. Because this is a conducting shell and therefore can enclose no net charge. Well, then you might say, wait a minute, that's a lie, because I know that this inner shell has some charge on it, and this sphere sure has charge on it. We know that, and I'm enclosing that sphere. Well, what that must mean then is that the net charge enclosed, if I draw a Gaussian surface in between B and C, and I draw inside that shell, everything I enclose, all of the net charge has to be 0. So if this has a charge of plus 2q, this inner shell then must have a charge of minus 2q, so that all of the charge that's enclosed, the net charge that's enclosed, is 0. Well, if this inner shell has a charge of minus 2q, and the total charge for the shell is minus q, it must mean that the outer shell has a charge of plus q. Plus q minus 2q gives me minus q. So that tells me I've answered the last question. Now what about the last field question. For r greater than c, now I'm enclosing the entire shell and sphere. In that case, the total net charge, I've got plus 2q for the sphere, minus q for the shell, so it's just going to be plus q. And of course, as you might expect, the field is just like a point charge. Q divided by 4 pi epsilon naught r squared. Because I'm enclosing both the sphere and the shell. If my Gaussian sphere has some radius r, which is larger than c, in that case, it just looks like a point charge again. So it's as though all of the charge from both the shell and the sphere were located right at the center of that sphere. Kind of an interesting application. Well, those are some fairly rudimentary examples of how to use Gauss's law. I'd like to do something that's a little bit more advanced now, but still works very well with your calculus skills and Gauss's law. Suppose we have a situation where we have a non-uniform charge distribution. So for example, suppose I have a sphere, but instead of me telling you that it's uniformly charged, I say, you know what, it's got a radius of r, but it has a charge distribution such that rho, the charge density, is equal to some constant rho naught times r for r less than or equal to capital R. And it has a charge distribution of 0 for r greater than r, anywhere else. And I say, find the electric field inside and outside that sphere. Let me point out a mistake that is made on every single Gauss's law test by at least one person every semester. The field outside this sphere is not 0. Yes, there is no charge outside the sphere, but if I draw a Gaussian sphere anywhere outside, I'm enclosing the entire sphere. So how could the field be 0? It can't be. Yet, every semester somebody always says, oh, I'm outside, so therefore the field is 0. Not true. If that were the case, how could you have a point charge? Because everything is outside a point charge. Somehow that's lost on some people. Anyway, let's find the field inside the sphere. So I'm going to draw a Gaussian sphere, give it some radius little r inside the sphere. Gauss's law still works. I can say the electric field dot dA is equal to the charge enclosed divided by epsilon naught integral. Once again, same rule applies. The field is constant at every point on this Gaussian sphere. The area vector and the electric field are both radially pointed outward in the same direction. So I can pull E outside. Integral of dA is going to be the area of that sphere. So immediately on the left side, I can write 4 pi r squared times E is going to give me Q enclosed over epsilon naught. But the question is, how much charge am I enclosing inside this? Well, I'm not enclosing all of the charge, and by the way, I don't know what the charge of the sphere is anyway. All I know is I have a charge density. So what I have to do, I have to take an extra step to use Gauss's law in this case. I can write my charge enclosed is equal to the integral of rho dV. In the case of a sphere, how do we get dV? Well, dV, I can write V for a sphere. Volume of a sphere is 4/3 pi r cubed. dV dr is 4 pi r squared. Therefore, dV is 4 pi r squared dr. So when I want to find out, when I want to calculate the enclosed charge, I'll take rho, which is rho naught times little r, multiply by 4 pi r squared dr, and integrate from 0 to little r, because that's how much charge I'm enclosing. This becomes integral 0 to r. Rho naught's a constant, I'll pull that outside. 4 pi is a constant, pull that outside. And I have r cubed dr. Integral of that is r to the 4th over 4, so I get pi rho naught r to the 4th when I put my limits in. That's going to be my charge enclosed. Now I can use Gauss's law, and I can say E times 4 pi r squared is equal to pi rho naught r to the 4th over epsilon naught. And then calculate E. E becomes, the pi's go away, and I have rho naught r squared over epsilon naught times 4. So that is my E field inside my non-uniformly charged sphere. I have to do the same procedure to find the field outside. In this case, I'm going to draw a Gaussian sphere outside. I'm going to give it, again, a radius little r. And in this case, I know that I'm enclosing all of the charge in that sphere. So to get Q enclosed, I'm integrating the integral of rho dv from 0 to big R, which I can write as rho naught little r 4 pi r squared dr, integral 0 to r. Notice, it's going to be the same answer as we got in the first part for the charge enclosed, except we're going to replace little r by big R. And so my charge enclosed is going to be pi rho naught capital R to the 4th power. To get my field then, once again, it's going to be electric field 4 pi little r squared, because I'm always using the radius of the Gaussian when I'm doing E dot dA, is equal to the charge enclosed pi rho naught r to the 4th over epsilon naught. And my electric field outside is going to be then rho naught divided by 4 epsilon naught little r squared. And on top I have rho naught times r, capital R to the 4th. So this is my electric field outside the sphere. Going to do one more example. In this case, let's do an insulating cylinder. Suppose I have an insulating cylinder of radius r. Let's say it has a non-uniform charge density, 1 over r, capital R, minus r over capital R squared. For 0 less than r, less than big R. And suppose I want to find the electric field both inside and outside the cylinder. Assumption is, and of course, for r greater than r, the charge density is 0, even though the field isn't 0. To find the field inside the cylinder, I can draw a Gaussian cylinder. And I can say that the charge enclosed by that Gaussian cylinder is equal to the integral of rho dv. For a cylinder, the volume is pi r squared times the length. And so dv would be equal to 2 pi rl dr. So to find the charge enclosed, I've got to integrate. Let's see, I'll pull the rho naught and the L out. I've got integral of 2 pi r dr over capital R minus integral dr over capital R squared times 2 pi r squared, all from 0 to little r. I can compute the integral. When I do that, I'll let you do that on your own. I'll get an enclosed charge of 2 pi rho naught L r squared over 2r minus r cubed over 3r squared. My electric field then, E times 2 pi RL is equal to Q enclosed over epsilon naught, which gives me an electric field of rho naught over epsilon naught R over 2R minus R squared over 3 capital R squared. So that's for inside. Outside the cylinder, once again, I have E times 2 pi RL, where R is outside the cylinder, so I draw another Gaussian cylinder that's outside the given cylinder. And that's going to be equal to the charge enclosed, which will be 2 pi rho naught L. But in this case, little r's get replaced by big R's, and I end up with R over 2 minus R over 3 for a field that's equal to rho naught R over 6 epsilon naught little r. A wrinkle on this is we can